In the last slide, I mentioned necessary insufficiency. So now I'm going to go into that a little bit more in detail. So a factor X is considered necessary if the disease Y never develops unless that factor X is present. X is considered a sufficient cause if Y always develops in the presence of X. Now there are 4 conditions under which X may cause Y, and they're listed here. Essentially, we can have the first condition where both X is necessary and sufficient. The second is when X is only necessary but not sufficient. The third is when it is not necessary but it is sufficient. And the fourth is when it's neither necessary nor sufficient. So now I'm going to go into what this all means. So the first condition, when X is necessary and sufficient to cause Y. That is, with X present, Y always occurs, and nothing but X is needed to cause Y. So it's a very stringent condition that truly doesn't exist in the natural biological world. It's very hard to think of a condition for which there's a factor that's both necessary and sufficient. The second condition is where X is necessary but not sufficient to cause Y. And this is where X must be present when Y is present, but Y is not always present when X is present. And that is, there's some additional factor that must also be present in order for Y to occur. Now, this is a condition that's probably more realistic in the general public health, right? You can think of probably several situations or diseases where there's some risk factor that is necessary to cause that disease, but it's not sufficient. Perhaps you could think of HIV and AIDS, right? HIV is the virus that is necessary in order for AIDS to occur, but it's probably not sufficient. There has to be some other factor, perhaps a predisposing factor, that exists at the individual level in order for the AIDS to occur. There could also be a precipitating factor at play in the relationship between having the HIV infection and the subsequent development of AIDS. The third condition is where X is not necessary, but it is sufficient to cause Y. That is, X always causes Y, but that Y has other causes that can occur without X. Now, there are lots of examples in public health that we can apply to this situation. I'll let you sit back and think about that. But again, it's when the risk factor X always causes Y, but that Y could be caused by other things as well. And then finally, the fourth condition is where X is neither necessary nor sufficient to cause Y. So X may or may not be present when Y is present. If X is present with Y, some additional factor must also be present. And this condition is the one that is the most common in epidemiology and public health. It's often true that there's some factor that causes some disease, but that there are other factors at play as well that are contributing to whether or not that disease occurs. Here is taking those 4 concepts and putting them into a 2x2 table, as we're used to doing now, where we have disease down the columns and the exposure status along the rows. And here we can think of A, B, C, D as in terms of the necessary and sufficiency conditions. So for example, if X is a sufficient cause of Y, then B is always going to be equal to 0. That is, you're never going to have a not diseased person who was exposed to that X factor, and because if X is sufficient to cause Y, Y will always occur when X is present. Another example is if X is a necessary cause of Y, then C is always 0. Here is where, unless X is present, then Y will not occur. So C would be 0 in the absence of X. And then the third example is if X is both necessary and sufficient for Y, then B and C are always going to be 0, right? So similar to the most recent example I gave, where if X is not present, then we're going to have no disease, so C will be 0. And if X is sufficient for Y, so in the presence of X, then you will not have not diseased people, right? Everyone will be diseased. So B would be 0 as well. And then finally, if X is neither necessary nor sufficient, again, the most common scenario in epidemiology, then none of the cells are going to be 0. So now I want to shift and get more specific and talk about causation in health. So as I've been saying, a causal agent or some exposure is rarely sufficient to cause the disease. There's almost always a need for multiple agents in order for the disease to occur. And that means that there are mixed effects among these agents that cannot be described using our simple definitions or criteria. That is, the last 4 examples I gave you. Those are very simple and really don't describe the true relationship between risk factors and disease in reality. In addition, time relationships vary, and they're complex and they're lengthy. And again, our 2x2 simplistic way of looking at things does not account for these time relationships. And then lastly, it's difficult to replicate exact results. And that is because controlled settings are rarely possible in public health. So here are just some scenarios to kind of think about this in a very kind of simple way, but hopefully a fun example. So scenario 1 is where you have an otherwise healthy man is admitted to a hospital with multiple fractures, having been hit by a bus just outside the hospital. So the question is there a causal relationship between being hit by a bus and having these multiple fractures? Well, hopefully your answer to this is yes. There's a short time frame between the exposure X, which is the being hit by a bus, and the outcome Y of multiple fractures, so the time relationship is short. The being hit by a bus is certainly sufficient to cause the multiple fractures, and in order to have the multiple fractures, he had to be hit by a bus, so it's also necessary. So a second scenario is where you have a woman with a persistent headache, gives a history of head injury some months ago. So the question is there a causal relationship between the woman's history of head injury and persistent headache? And this may not be as obvious, right? It may or may not be the case that history of that injury is what's contributing to her headache. Depends on the duration of time between the injury and the headaches, right? It also depends upon other factors at play. The individual's predisposing factors, perhaps precipitating factors that might be contributing to her headache. Also, did she have headaches before her head injury? Those are all the things that have to be accounted for. And then finally, another scenario is Aunt Sally is alive and well at age 100, and she has smoked 20 cigarettes per day since the age of 18. Is there a causal relationship between smoking and longevity? Well, hopefully your answer to this is an absolute no. And this is an example of where correlation is not causation. So it is incorrect to base the definition of causation on the limiting case of the necessary insufficiencies clause, which I mentioned a moment ago. So therefore, we need better or other definitions for causation. The one given by Evans, who's an epidemiologist as well, said that a factor is a cause of an event if its operation increases the frequency of the event. So that kind of makes sense, and that's this idea of a dose response. I increase some exposure that may increase the risk or the frequency of that event. However, that is kind of a limited definition, really, because it lacks in some of the other things that we're going to talk about later when we get into the Bradford-Hill criteria. Now, Rothman has another definition for causation, which is that a cause of a disease is an event or condition or some characteristic that plays an essential role in producing an occurrence of the disease. Now, the key part of this is that he says an essential role, but we have to define what that means. So what is essential? And here you can imagine that definition could vary across different disease states as well as different types of exposure, right? But I think that the idea is moving toward a more specific definition of causation that isn't so absolute like that necessary and sufficient criteria that we've been talking about. That moves us to now discussing the sufficient component cause model. And this is a model described by Rothman as well. And basically this is a multifactorial model of causation. And it's given in this kind of pie diagram with the idea that each component of the pie contributes to the disease, the outcome, and that each component of the pie is contributing a certain amount to the overall risk of disease. So each pie is a causal mechanism, so it is a sufficient cause for the disease, but it isn't necessary itself. And that this goes into the idea that a disease has multiple causal mechanisms, and we know that for most things, right? It's, for example, lung cancer. There are more than one way. There are more than one way to develop lung cancer. So there are multiple causal mechanisms there. And so each letter represents a causal factor that is a component of that overall causal mechanism. A given causal mechanism requires the joint action of several component factors. In the example given here, where you have 3 different causal mechanisms, 1, 2, and 3, you notice that the A factor is present in all 3 of those models. So in this example, A is a necessary cause, since it's present in all 3 causal mechanisms, or causal pies. However, each causal pie consists of different risk factors, right? In the first one, you have A, B, C, D, E, and in the other 2, you have different combinations of different factors. But again, all 3 of those do contribute to the disease occurring. Now, again, this, like the others, is a theoretical construct. However, this is the way that we should be thinking about diseases and risk factors and diseases in epidemiology. And finally, these causal mechanisms that are shown in this slide aren't derived from empirical data. This is merely conceptual. Going further into that, as I said, each pi of the causal mechanism represents a sufficient cause. It represents a set of minimal conditions and events that inevitably do produce the disease. And a complete causal mechanism consists of a constellation of component causes that requires a joint action of its component causes, and that each component plays a necessary role. And a necessary cause is a component cause in every causal mechanism, and that, going back to the prior slide, that would be A, whereby each pi, that component cause is present, and if absent, then the disease does not occur. Now, some implications of the causal pi model. The strength of a component cause depends on the prevalence in the population of the other component causes in that overall causal mechanism. So a particular factor may appear to have a strong effect if the other component causes are more common in that population, or it could appear to have a weak effect if the other component causes are rare in the population, and that is because in order for the disease to occur, each of those components of the causal mechanism must be present at a particular prevalence in order for the relationship to occur among those causal factors to contribute to the disease. No component cause in the causal pi model acts alone. Every case of disease is a result of multiple component causes acting jointly in a causal pi. And importantly, the causal mechanism does differ among individuals, right? So therefore, in each case of a disease could be attributed to each of the separate component causes that make up that causal mechanism. And importantly, the sum of the fractions of a disease attributable to each of the causes does not necessarily equal 100%. There essentially is no upper bound on those fractions contributing to the overall disease.